Okay, so we're going to start off with a probability question. Say you work at a shoe factory and you're working on creating boxes with pairs of shoes. Currently in front of you, imagine there are three pairs of shoes for a total of six individual shoes with the following sizes: two size 4s, two size 5s, and two size 6s. The factory defines an acceptable pair as two shoes that differ in size by a maximum of one size. So a shoe with a size 5 and a shoe with a size 6 would count as an acceptable pair. If you close your eyes and randomly pick three pairs of shoes without replacement, what is the probability that you end up drawing three acceptable pairs?
Okay, so let's see. So we have these six shoes, size 4, 5, and 6, and you're saying we pick three pairs using just these six shoes only. There's no replacement or anything like that.
Agreed?
Okay. So in that case, let's see. So if you said that the acceptable pairs differ by one size, then I guess you could have pairs that are both of the same size, like say 4 and 4, or you could also have pairs like 4, 5, or 5, 6. And in fact, I think what I noticed is that the only illegal pair would be 1, 4 and 1, 6. And so I think that's something I noticed straight away. And so I guess in terms of finding the probability that these three pairs of shoes will work, I think one way to do that would be to actually count the complement, or the cases where you do have 4 and a 6 together, and kind of find the probability of that happening over all the cases.
Like we've covered in the lecture videos in the last modules, right off the bat, the candidate realizes that solving for the complement could be a very straightforward approach. Having a good understanding of the various approaches that we've discussed in the course is incredibly important and will speed you right up. Right when the interviewer tells you the question, you'll have an intuition for what strategy or direction is likely to be favorable. As you get through the course, you're going to be able to answer even the most challenging of quant interview questions within minutes, because you'll have the intuition needed to know what direction makes the most sense. And if that direction doesn't yield results, you'll be able to go down your tool belt to the next strategy for approaching the question. Let's continue with the interview.
Like you said, I think calculating the complement is a great idea. Go ahead.
Yeah, so I guess I'll just start counting that. And I think one way we could think about picking these three pairs is if we kind of ordered these six shoes in a line and just took 1 and 2 together to be a pair, 3 and 4 are a pair, and 5 and 6 are a pair. So in that case, we would have 6 factorial, which is 720 cases in total for the number of pairings we could do. And out of these, we want to count how many that have a pair of 4 and 6. So I think we can count this like this. So say we have these three pairs, and we want one of them to be this 4 and 6 pair. So first of all, we have to pick which of these three pairs is going to be that pair, the 4 and 6. So that's three possibilities for that. And in that 4 and 6 pair, we also need to pick the ordering. So it could be 4, 6 or 6, 4. So that's two possibilities. And we also need to pick which which size 4 shoe it is of the two, which is another 2, and same for 6, so another 2. So in total, that's 3 times 2 times 2 times 2. And as for the other 4 shoes that are left, there's 4 factorial ways to order them in the remaining 4 spots. So in total, this would be 24 times 24, which is 96, and that will be 576 ways to pick these shoes that have a 4 and a 6 pair in them. And I think one other thing is that there's actually two pairs of fours and two pairs of sixes. So it could be possible that there's multiple 4-6 pairs inside these three pairs of shoes that we pick. And in that case, we would be double counting those in this method that we just did. So to account for that, I think we should also count the number of pairings that have two pairs of a 4 and a 6, and then subtract that from the number we just got. So to count that, that's fairly straightforward because the only possible pairs are 4-6, 4-6, and 5-5. So we need to pick, again, which of the pairs is the double 5 pair. As for the other two pairs, we need to pick basically which 4 goes in the first 4-6 pair and which 6 goes in the first 4-6 pair. So that's 2 times 2. And there's also the problem of ordering between 4-6 and 6-4 for both. So that's another 2 times 2. And and also as well for the 5-5 pair, we would need to account for the two different ways we could pick those. And so in total, this looks like 3 times 2 to the 5th, which is 3 times 32, or 96 pairings that have 2 4-6 pairs. And so if we subtract this from the number we got earlier, then that would leave us with 480 pairs in total that we don't want. And so out of 720, if we subtract those, then we're left with 240 pairs that are legal, and we would have a 1/3 probability, 240 over 720, of randomly picking 3 pairs that have that kind of fit the conditions that we're given.
Great job. That is correct.
Let's walk through how to come to this answer. If you've enrolled in the course, you'll see this is actually very similar to number 13 in the course's probability interview questions bank. The candidate found the complement to answer this question. Let's look at another totally reasonable way to answer this question. As the candidate mentions, the only configuration that is not acceptable is the 4 and 6 configuration. Therefore, we can find the probability of the following 2 mutually exclusive events. Say that we label the shoes instead of 4, 4, 5, 5, 6, and 6 as A1, A2, B1, B2, C1, and C2. In the first case, the 4s are paired together, meaning that A1 and A2 are paired together. A1 is just as likely to be paired with any of the other 5 shoes, so the probability that it's paired with A2 is 1 in 5. The second case is where the 2 size 4s are each paired with a size 5. So in this case, we want the probability that A1 is paired with one of B1 and B2, and then A2 is paired with the other of B1 and B2. This can be written as the probability that A1 is paired with one of B1 and B2, and A2 is paired with the other of them. We know from the lectures and Bayes' rule that this can be rewritten as the probability that A1 is paired with one of B1 and B2 times the probability that A2 is paired with the other of them, given A1 is paired with one of B1 and B2. The first term is equal to 2 over 5, since A1 is just as likely to be paired with any other shoe. So there's a 2 over 5 chance that it's one of B1 or B2. Given that A1 is paired with B1 or B2, that leaves 3 equally likely shoes for A2 to be paired with, only one of which is a B shoe, or size 5. So that happens with a 1 over 3 probability. Case 2 therefore gives us a 2 over 15 probability. Summing up these two cases, we get 1 over 5 plus 2 over 15 equals 1 over 3. In the written solution to this question, you'll see this approach in detail, and another approach using complements. Make sure you understand both of these. At the bottom of the solution, you'll see a simulation run for this, and that also checks out and shows us that as the number of trials approaches infinity, this final probability approaches 1 over 3.
Okay, so let's change gears. I'm going to ask you a totally new question involving a coin. So let's say you are flipping a fair coin until you obtain your first heads. If the first heads occurs on the kth flip, we're given k balls. We're going to put these k balls into 3 bins, labeled 1, 2, and 3, totally randomly. You want to find the probability that none of these 3 bins end up empty.
Okay, so just to clarify, so k is the number of the flip that we first see heads on. And we're not given any balls for any of the previous flips, just that one.
Yes, k represents the flip number on which we first get the heads. And so after flipping that heads, we are then given k balls.
Okay, so yeah, I guess, so if we are given k balls, I think the first thing would be to kind of calculate the probability of getting any of these numbers of balls. So for instance, there's a 1/2 probability that you'll see a heads on the first flip, so you'll just have 1 ball. And for every flip after that, you'll have half of that probability for getting that number of balls. So for 2 balls, for instance, it would be 1 over 4 and so on.
That makes sense, yeah.
Okay, and so for the bins, there's always 3 bins, is that correct?
Correct. Just 3 fixed bins.
Okay, so let's see.
Let's pause for 10 seconds. To do well on quant interviews, you need an unwavering intuition for probability, EV, betting, strategy, market making, brain teasers, and more. If you want to develop this intuition, learn the fundamental math theory to crush every type of quant interview question, see hundreds of pages of guides and solutions, talk to real quants, and so much more, then head over to thequantguide.com and enroll now.
Correct. Just 3 fixed bins.
Okay, so let's see. Yeah, so again, if we want to find the probability that none of these bins end up empty, then I think we could do a similar counting method where we kind of count instead the cases where there is at least 1 bin that is empty. And so let's see. So 1, 2, 3. Okay. Yeah. So with these 3 bins, suppose we have k of these balls, then the probability that one of these bins will end up empty would essentially be basically the way we could count that is there's 3 sort of choices for the bin that is left empty, and the k balls then could be distributed anyway within the other 2 bins that are left. So essentially that's 3 times 2 to the k for the number of ways we can distribute these balls in these 2 bins, and that's out of a total of 3 to the k possibilities. And so that would be kind of the number of ways we can do that, leaving 1 bin empty. But this also kind of double counts the basically cases where there's 2 of these bins are empty, because you could also have all the balls go into 1 bin. And that would basically, I mean, there's only 3 possibilities for that. And so we would just have to subtract those 3 possibilities from the initial count that we did.
Okay.
Yeah, so in total we have a probability with k-balls of 3 times 2 to the k minus 3 over 3 to the k, which is also 2 to the k minus 1 over 3 to the k minus 1. And so let's see. So yeah, we can split this up into 2 fractions, which is 2 to the k and 3 to the k minus 1, and negative 1 over 3 to the k minus 1. And if we combine this with the probabilities of getting each of the k-balls, then let's see. So that's 1. So you'll have k-balls with probability 1 over 2 to the k. So we just need to multiply that to this. So I think that leaves us with this sum of 1 over 3 to the k minus 1 minus 3 over 6 to the k. And this is the sum from k equals 1 to infinity. And so we can just do this as an infinite geometric series for both of these fractions. And so that would give, yeah, so I think in total that gives 15 over 10 minus 6 over 10, which would be 9 over 10.
Okay, so what does this 9 over 10 represent?
Yeah, so yeah, I think 9 over 10 is the probability that you have at least one bucket empty. And so the complement of that would be the probability that you have every bucket full, which is 1 over 10.
Awesome. Looks good to me. Do you want to just briefly walk me through your methodology?
Yeah, so I think for this problem, there's kind of 2 components to the probability, which is the probability of getting the k-balls, which is what the coin is doing, and then given these k-balls, the probability that you'll be able to cover all these buckets that you have. And so as for the probability of having k-balls is fairly simple. There's a 1/2 chance that you'll end up with 1 ball if you flip a heads on the first try, and then thereafter you have half of that for every increasing number of balls. So for example, there's a 1 over 4 probability of having 2 balls, 1 over 8 of having 3 balls, and so on, which is 1 over 2k. For the buckets, filling the buckets, I want to count essentially the number of ways we can leave at least one bucket empty, which is the complement of what we want. So in order to do that, I sort of imagined this scenario of having one of these 3 buckets empty, and so there's 3 choices for which bucket to leave empty, and then we count essentially the number of ways we can fill the other 2 buckets. So given each ball, there's 2 choices. So with k balls, there's 2 to the k ways we can make that distribution. And since this also double counts the cases in which 2 of the buckets are empty and all the balls are in one of them, we have to subtract that from the total number of cases. So that's 3 times 2 to the k minus 3 over 3 to the k possible distributions of these balls. And finally, we can multiply this by the probability of having these k balls, which is 1 over 2k. And if we do that, this actually simplifies out to a nice kind of two fractions, which is 1 over 3 to the k minus 1, and then minus 3 over 6 to the k. And then we can essentially just sum that with k from 1 to infinity, just as a standard geometric series. And that gives us 9 over 10, which again is the complement of the probability that we want. And subtracting it from 1 gives us 1 over 10.
This is a fairly involved question. As you work through this module and the questions associated with it, you'll be able to come to the solutions within a couple of minutes. Let's discuss the theory of how we got here. There are two important aspects to this question. One is finding the probability that we end up with k balls. So we know that for a fixed value k, the first head occurs on flip k exactly when the first k minus 1 flips yield a tails, and the kth flip yields a heads. These k events are all independent and each have a 1 over 2 probability. Therefore, the probability that the first head occurs on flip k equals 1 over 2 to the k. The probability that no bins are empty, given that the first head occurs on flip k, is equal to the probability that no bins are empty, given k balls are placed into the bins. We can calculate this by determining the probability of the complementary event. The probability that at least one bin is empty, given k balls are placed into the bins. To calculate this, we can use the principle of inclusion-exclusion. With k balls, the probability that any bin I remains empty is 2 over 3 to the k, because each ball goes into one of the other bins with probability 2 over 3. This is true for all three choices of one empty bin, giving 3 times 2 over 3 to the k. However, this overcounts cases when 2 of the bins remain empty. For example, the scenarios where bins 1 and 2 remain empty are counted twice. Once when counting 2 over 3 to the k for bin 1 being empty, and once again when counting 2 over 3 to the k for bin 2 being empty. We correct for overcounting these parts of the probability space, which is counted twice, by subtracting their probability once. For example, the probability of bins 1 and 2 being empty, so all balls go in bin 3, is 1 over 3 to the k. This is true for all 3 choose 2 or 3 pairs of balls. So we subtract 3 choose 2 times 1 over 3 to the k. The answer is asking us to solve for the complement of this value. Here's the detailed math, but once we simplify this series, we end up getting 1 over 10. At the bottom of the solution in the course, also check out the code for this simulation. You'll see that as the number of trials approaches infinity, this probability also approaches 1 over 10. Well, we're done. In the course, you've learned how to answer these questions and many that are significantly more challenging. Keep going through the mock interview videos and get through the questions and detailed solutions for this section, and you will be an absolute veteran when it comes to these interview questions.